Hello, this is Dr. Kraus. I'm going to record maybe a couple, maybe who knows, a few root locus example videos at the request of my students. Since this is the first one, I want to do a real brief overview of how I think about sketching a root locus. Certainly there's lots of videos on the internet that will go into more detail. And if you've got no understanding of root locus, you should probably go watch one of those first. So assuming you're at least mildly familiar, this is mostly a review. In my mind, so certainly different people have different numbers of rules that you have to follow when you're doing the sketching, and all of that is mostly fine. It's a little bit too much memorization for my tastes. Ultimately, to me, the root locus boils down to two things. You're going to start at the open loop poles. Each branch will start at an open loop pole and then end either at an open loop 0 or go off to infinity. So you got to know that where it starts and where it ends is important. And you got to find the open loop poles and the open loop zeros to do that. And then you got to satisfy the phase condition everywhere on all branches. And so those two things are enough to deduce any rules that you would need. So I use Feedback Control of Dynamic Systems by Franklin Powell and Amama Naini in my class, any edition really. It's a really solid book. And so the rules vary just a little bit whether you go with the most recent edition or an older edition. But like I said, rule 1, we start at the open loop poles and end at the open loop zeros or go off to infinity. Then there's the real axis. And again, this boils down to which points on the real axis satisfy the phase condition. And those are the points that are to the left of an odd number of real poles and zeros. Then, when we go off to infinity, we still have to satisfy the phase condition. And so if there are m zeros and n poles, then m of the poles will be canceled by the zeros, and you're left with n minus m uncanceled poles that go off to infinity, and they have to go off to infinity in a way that satisfies the phase condition. And then you find your departure and arrival angles by satisfying the phase condition near a pole or a zero. And then the break-in and breakout points, there's a more complex derivation there that doesn't really come from my 2 bullet points, except that recognizing which sections of the real axis must have either a break-in or a breakout point comes from the first bullet point. So with that, I've written a random root locus generator that's available on pip. And so if you install that, pip install random root locus generator, sorry about the super long name. And then I can randomly generate a transfer function. And so here's a simple one for our first example. And so it has 2 complex conjugate poles and 1 purely real 0. And so if I jump over to my document cam, the 0 was at -4. And the poles are at roughly -3, 9-ish. So, looks something like that. 0, complex conjugate pair of poles, real 0. So, I know that the part of my real axis to the left of an odd number of poles and zeros is on my real axis. The reason for that is if there's an angle contributed from each pole, those two cancel each other. And the angle contributed by the 0 is 180. And so I know that the phase of my transfer function at any point is the sum of the angles from my zeros minus the sum of the angles from my poles. Like I said, these two add to 360, so they don't matter. And if I'm on the real axis, then that phase condition has to be satisfied. So this point has a phase of 180, anything to the left of that 0. Next, rule 2 tells me, I did rule 2, I'm sorry. Rule 3 tells me that I have n minus m asymptotes. And so in our case, n minus m is equal to 1. So if I take plus or minus 180 plus or minus Q360 and divide that by n minus m, I get that I have one asymptote at an angle of 180 degrees. Well, that makes sense. This is my asymptote. Now, this is an ending point, and infinity is an ending point. So I must have a break-in point somewhere on this line. And so the branches of my root locus are going to start at my poles. They've got to come somewhere over here to where they're going to break in, and then one of them is going to head this way and one of them is going to head that way. Now, I tell my students, your professor might have different opinions, that finding this exact location by hand isn't really worthwhile. I want you to know that roughly what the shape is, and that should be to the left of this 0. And the rest of that, then, any other things that I would need to know about this root locus, maybe these go off at a slightly different angle, but I don't think it significantly affects the root locus. This is a solid hand sketch. And then, again, I'm not super concerned with departure or arrival angles. I mean, I know this arrival angle is 180. I could find those if I wanted to. I don't think that detail is going to significantly affect the accuracy of my sketch, and I know that there's a break-in point there. Then if I go back to Python, and I want to do a control utils, oops, and there's a root locus method built into the control module. I just don't like it quite as much as my own, although my own does require me to do some scaling and whatnot. I don't know. I have my own finicky preferences about what a root locus should look like. So that seems to be a confirmation that for this simple example with 1 real 0 and 2 complex poles, I have correctly sketched my root locus by hand. I'll do 1 or 2 more quick examples and upload those shortly.